Hi there, I'm Jeremy Krug, and in this section we're going to be taking a look at integrated rate laws, which give us another tool in order to determine the order of a reaction with respect to a certain reactant. Now, in our last video, we learned about how you can essentially take 2 or 3 or 4 different experiments and use those multiple experiments to determine the order. Well, in this method, all we have to do is actually have one experiment. Now, what you want to do is take the reactant that you're trying to determine the order of, and let's make some graphs. The first graph we're going to make is the concentration of the reactant on the y-axis and time on the x-axis. And so if you do that, there's a chance that the graph might look something like this. If you find that that plot is a straight line, like we have right here, that means the reaction is 0th order. Now, we haven't talked much about that, but essentially what that means is the concentration just decreases steadily over time. It doesn't really have any other factor that is affecting it. Now, if that's the case, then the rate law is going to be rate equals K times the reactant raised to the 0 power. Now, you probably know that anything raised to the 0 power is just equal to 1, which means rate equals K. And so the rate is just whatever the rate constant is. Now, if that's the case, you'll find that the rate constant, K, is equal to whatever the absolute value of the slope of that line is. So in simple algebra, you probably have learned how to determine the slope of a line, rise over run. So you could just calculate that just graphically and then take the absolute value of that, and that would be your rate constant. Now, notice the word here, if. I said if the plot is a straight line. That means there's a good chance it's not going to be a straight line. Now, if that's the case, then let's make another graph. The next graph that you would want to make is a plot of the natural logarithm of concentration of the reactant versus time. So you make another graph. So natural log of the reactant would be plotted on the y-axis rather, and time is plotted on the x-axis. And if that graph gives you a straight line, then the reaction is first order. And if that's the case, then the rate law is just going to be rate equals K times the reactant raised to the first power. So rate equals K times the reactant, A in this case. And if you want to find the rate constant, well, same way as you did it the other time it was a straight line. Just take the slope of the straight line, rise over run, and then take the absolute value of that slope, and that's going to be the rate constant. Now, once again, we have that word if in here again. That means there's a pretty good chance that this is not going to be a straight line either. So if that's the case, well, then you have to make yet another graph, a third graph. And in this one, you're going to make a graph of the reciprocal of concentration of the reactant versus time. So basically 1 over A versus time. And if you do that, and the graph looks like this, and it's a nice straight line, then we say the reaction is second order. So we have 3 possible graphs that you could make. Concentration versus time, natural log of concentration versus time, reciprocal of concentration versus time. Only one of those is going to be a straight line. If this one's a straight line, it's second order. Now, if that's the case, then the rate law is going to be rate equals K times A to the second power. You know, that 2 is there because it's second order. And the rate constant is determined the same way as it was in the other ones. It's just take the slope of the line, and since it's a positive slope, the rate constant is just equal to the slope of the line. Now, to keep things consistent, I wrote it's equal to the absolute value of the slope of the line, because that's true, that's mathematically correct. Just to keep it consistent among 0, first, and second order. But since it's positive, K is just equal to the slope. And so you can determine the order of a reactant in a reaction just by doing this graphically. Now, let's try an example problem here. Here we have a reaction. 2NO2 yields N2 plus 2O2 is studied. The following graphs are produced and used to analyze the reaction. So part A asks, what is the order of this reaction with respect to NO2? Now, we have these three graphs. We want to look for the straight line graph. Do you see the straight line? It's the third graph, isn't it? This one right here. And the straight line is the 1 over NO2. Now, do you remember the reciprocal, 1 over the concentration versus time? What order does that mean? Well, that was second order, wasn't it? So this is a second order process. Whenever you're thinking about these, concentration, if that had been a straight line, this one over here, it would have been 0 order. Natural log, that's like secret code for first order. So if this graph had been a straight line, it would have been first order. 1 over concentration, that is secret code for second order. So since this is a straight line, it's a second order graph. You have to know that. The College Board does not tell you that information on the AP exam, so you have to be able to keep all this straight. Now let's write the rate law. Well, there's only one reactant, so this is pretty straightforward. Rate equals K times NO2, and since it's second order, it's squared. So put that little squared up there. Now, this is how we determine the order of something graphically. Now, we're going to take this one step further, and we're going to do part C, and let's determine the rate constant for this reaction with appropriate units. So now to do this, we have to find the slope of that line. Now, this is kind of an inexact science since we have, it's graphical, so we'll just do our best here. And I'm going to use these first 2 points right here. We have a point right here, a point right here. I would say that this point right here is at the ordered pair. It looks like it's about 60, 150. And this point right here is at the ordered pair 0, 100. So all I have to do is take rise over run. So the y's, that's 50, and my units are molarity to the minus 1, over the change in x, which is 60 minus 0, that's 60, and my units on the x-axis are seconds. And so when I divide this out, 50 divided by 60, I believe, is about 0.83, and that's molarity to the minus 1. If I bring the seconds to the numerator, it becomes seconds to the minus 1 as well. So there I have the rate constant, just the slope. Don't forget to put the units in there as well. Now, let's take this yet a step further. We're going to look at a special type of equation that's actually going to help us to calculate how much of a reactant is present after a certain amount of time. And this is something called an integrated rate law. We can actually use these, and this is actually very neat. We can calculate the concentration at any time throughout the reaction. Now, if we have a first order process, rate equals K times A, we can use calculus and integrate this equation here into something that looks like this. Natural log of A sub t minus natural log of A sub 0 equals negative KT. Now, you don't have to know the calculus. That's the nice part about this. If you take physical chemistry in college, you'll see how this works. But for right now, just take my word for it that that is the first order integrated rate law. Now, A sub t represents the concentration of reactant A at time t. After how many t seconds or t minutes have gone by. A sub 0 represents the concentration at time 0. And that's just an arbitrary time. That could be the time that you start the reaction. It could be some other time. It could be at the point when you start your stopwatch. It's just the starting time. Now K, that's the rate constant. We've worked with that a little bit already in this unit. And then T is the time that has elapsed. So we're going to solve a couple problems with this first order integrated rate law. And let's see how we can do that. So a first order reaction has a rate constant of 3.8 times 10 to the minus second reciprocal seconds at 270 kelvins. If the reactant begins with a concentration of 0.50 molar, what will be the concentration after 60 seconds? So once again, we're going to use the first order integrated rate law, and we're just going to plug and chug. Now, notice we're trying to find the concentration after 60 seconds have elapsed. So we're solving for A sub t. So that's our unknown in this equation. Now A sub 0, that's the concentration at the beginning. Now that's why there's this little 0 there. So what's the concentration at the beginning? Well, it says it's 0.50. So I'm going to plug that in there. Now the rate constant, the K, is given to us, 3.8 times 10 to the negative 2. And the T is for time. It says after 60 seconds. So we're going to plug the 60 in there. So now all we have to do is use algebra to solve for A sub t. So on the right side, using my calculator, I get negative 2.28. The natural log of 0.5 is negative 0.693. Be very careful with your signs here because we have a minus and negative, so that's actually a positive. So when I subtract 0.693 from both sides, I get natural log of A sub t equals about negative 2.973. And so now all I have to do is take the inverse natural log of negative 2.973. On your calculator, there is an e to the x button. Probably it's on the second natural log button, so just click that. And if you evaluate this, you'll find that A sub t is about 0.051 molar. And so that's the answer. And that makes sense because if we're starting out at 0.50 molar, you'd expect the concentration after 60 seconds to be somewhat less than that. So this is an answer that does make sense. If you're doing these problems and you ever get a concentration that's a negative number, well, that doesn't make sense. That's not possible. So you know that you had done something wrong if that were the case. Or if the concentration were, higher than 0.50, reactants shouldn't do that. Let's try another example here. A first order process at 300 kelvins is measured. If the reactant's concentration drops from 0.95 molar to 0.45 molar in 170 seconds, what is the rate constant? So now we're going to use that same first order integrated rate law, and we're going to plug and chug again. So A sub t, that's the ending concentration, so that's 0.45. We'll plug that in. And then the A sub 0 is my starting concentration, so that's 0.95. And the K is what we're solving for this time, so that's my unknown. The time is 170 seconds. So now I can just use my calculator and algebra, of course, to solve for K. So natural log of 0.45 is negative 0.799. Natural log of 0.95 is negative 0.0513. And then I have the right side over here. I'm going to evaluate all this on the left side. That's negative 0.7477. And on the right side, I still have my negative 170K. So when I solve for K, I get an answer of 4.4 times 10 to the negative third reciprocal seconds. So that's how I solve this problem here using the integrated rate law. Now, another very important function as far as determining how much of something is left and how long it takes for it to decay is called the half-life. And this is especially very important for first-order processes. Now, an important first-order process that takes place in the natural world is nuclear decay. And probably when you hear the word half-life or the phrase half-life, you're probably going to think of nuclear decay. And for these first-order processes, we're often interested in how long it takes for half of an initial reactant to be depleted. And the time it takes for exactly half of a reactant to be depleted is called the half-life. Now, we're going to derive that equation. for half-life, and we're going to start with the integrated rate law for first order. Now in this video course, I don't derive a whole lot of equations. This is one of just a couple that I actually derive in the whole 100 and some odd video series. So I think this is kind of fairly important and fairly interesting. Now, hopefully you'll agree that at the half-life, A sub t is just equal to whatever you started with, A sub 0, divided by 2, right? So if that's the case, then this is also a true statement, that the natural log of A sub 0 divided by 2 is the same thing as natural log of AT at the half-life, isn't it? So I'm going to just plug that in there, and everything else is the same. And since we're talking about half-life, I've just substituted in a little abbreviation for half-life. We'll call that T sub 1/2. Now, at this point, there is a property of logarithms that says log of x divided by y is equal to log x minus log y. So I'm going to carry that out with this little division over here. Natural log of A sub 0 divided by 2 is equal to natural log of A sub 0 minus natural log of 2. And of course, the rest of that equation is intact. Now you might notice that we have natural log of A sub 0 minus natural log of A sub 0. So I can actually cancel those out. And I can do a little sign change here. And what I'm left with is the natural log of the number 2 equals the rate constant times the half-life. And so if I'm interested in the half-life, I just divide both sides by k and figure out what natural log of 2 is on my calculator, and I can find out that the half-life for any first order process is equal to the number 0.693 divided by k. And that's my half-life equation. Pretty neat little equation. Hopefully you can see how we get that now. Now we're going to use that equation to solve a half-life problem. In the previous problem, the first order reaction had a rate constant of 4.4 times 10 to the third reciprocal seconds. What is the half-life of this process in seconds? Well, if we know the rate constant, all we've got to do is plug it into that equation right there. So plug it in, and if you take 0.693 divided by 4.4 times 10 to the third reciprocal seconds, you find that the half-life is equal to 158 seconds. So, just over, 2.5 minutes approximately. So there we have the half-life. Now, we've been looking at the first order integrated rate law, and of course a half-life equation derived from that. Well, we're going to look at the second order integrated rate law as well. Now this is what that looks like. 1 over A sub t minus 1 over A sub 0 equals kt. So we just use this for second order processes. And once again, this is just a plug and chug, just like it was for first order. Let's try this example. A second order process has a rate constant of 2.6 times 10 to the negative second reciprocal molarity reciprocal seconds. If reactant A has an initial concentration of 0.80 molar, how long will it take for its concentration to drop to 0.10 molar? So once again, we're just going to plug and chug into the equation here. The A sub t is the final concentration, right? So that's the 0.10. So we're going to plug that in for A sub t. And the starting concentration is A sub 0, which is 0.80 molar. So I'm going to plug that in for A sub 0. It tells me what the rate constant is. The K is 2.6 times 10 to the negative second. So I'm going to plug that in there. And of course, I'm solving for t. So now I just have to, solve on my calculator and using algebra. So the reciprocal of 0.1 is 10, and then the reciprocal of 0.80 is 1.25. So I have this. When I subtract that out, I get 8.75 equals 2.6 times 10 to the minus second times t. And when I divide this out, I find that the answer for t is about 337 seconds. And so that's my answer. That's how long it's going to take for this concentration to drop by that amount. So that's how we work a problem with a second order integrated rate law. There is even a zero order integrated rate law. But if you can work with first and second, working with zero order is very simple. In fact, here's just a very brief summary of everything we've looked at in this section about integrated rate laws. For zero order, there's your rate law. There are your units for K. If you ever had to use the integrated rate law for zero order, that's what it is. It's actually very straightforward, just plug and chug. Here's your first order information, rate law, units for K, integrated rate law, and there it is for second order. So, these integrated rate laws are just plugging it in using algebra. I think that that's something that most AP chemistry students can do, especially if they're given those equations, which they will be given those on the AP exam. Thanks for watching. Hope you learned something here. This is kind of a long video, but there's a lot going on here with this section. If you learned something, please hit that thumbs up button and join me in my next video where we're going to take a look at the next few sections of chemical kinetics.